Welcome to this deep dive. Today, we're going to be pulling back the curtain a bit on how we actually build the world around us.
Right. The places we live and work in.
Exactly. We've got some great material here that really digs into, the fundamentals of construction. Everything from the ground up, literally, to the roof.
It covers quite a bit, yeah.
So the goal today is really to understand those essential bits and pieces that, well, make our buildings work, make them stand up.
It's fascinating stuff when you get into it. Things we often take for granted.
Absolutely. I'm really looking forward to digging into this.
Me too. Where should we start?
Well, let's start with something absolutely basic, something we see everywhere. Concrete. What's like the core recipe for that?
Okay, concrete. Yeah, super common.
Yeah.
In its simplest form, it's really just cement, sand, gravel, and water.
Just those four things.
Pretty much. The cement acts like a glue. When you add the water, it starts a chemical reaction, and that binds all the sand and gravel together into this hard, solid mass.
Okay, simple ingredients, powerful result. Now, thinking about actually mixing it, maybe in a smaller site, what are the really basic tools involved?
Oh, for small batches, you're looking at the classics. A shovel, probably, to mix everything together, and a wheelbarrow to move the wet concrete around.
Right, very hands-on. You can almost picture the effort involved.
Definitely gives you that feel for, traditional construction work.
So, you've mixed your concrete. How do you know if it's actually any good? If it's going to do the job? I see there are a couple of tests mentioned.
Ah, yes. Quality control is key. There are two main tests. The slump test and the compression test. They tell you different things.
Okay, slump test first. What's that measuring? Workability, it says here.
Yeah, workability.
Yeah.
Which basically means how easily the concrete flows, how easy it is to place it into the forms and shape it. You don't want it too stiff, but you definitely don't want it too sloppy either.
Like pancake batter. Getting that right consistency.
That's a perfect analogy, actually. Yeah. You want it pourable, but not so runny. It just spreads out into a puddle.
Got it. And the other one, the compression test. That sounds like it's about strength.
Exactly. That's all about how much load the hardened concrete can take before it, crushes.
And why is that so critical?
Yeah.
Seems obvious, but...
Well, the concrete has to support everything above it, right? The weight of the building itself, people, furniture, snow on the roof, everything. If it's not strong enough, the whole structure could be compromised.
Makes sense. You need different strengths for different buildings, I imagine.
Oh, absolutely. The concrete in a skyscraper foundation needs way, way higher compressive strength than, say, the concrete for a garden path. The use dictates the required strength.
Right. Okay, let's go back to that slump test. It mentions different results. True slump. What does that mean?
A true slump is usually the target. It means the cone of concrete slumps down evenly when you lift the mold off, holding its shape pretty well. It tells you the mix is well-balanced, workable, good for general use.
So that's the Goldilocks zone, sort of.
Pretty much, yeah. Sweet spot.
Then there's shear slump. That sounds less good.
It is less good. Shear slump is when one side of the cone sort of slides down or shears off. It usually means the mix isn't cohesive, maybe unbalanced. It could lead to uneven setting, potential weak spots, maybe cracks later on.
Definitely something to avoid.
Yeah.
And collapse slump. That sounds even worse.
Oh, that's the worst. Collapse slump means the mix is way too wet. The concrete just completely loses its shape and collapses when you lift the cone. It signifies a really poor mix, very weak. You wouldn't want to build anything structural with that.
Right, so those tests are like the gatekeepers for quality concrete. Okay, moving down. Foundations. This is literally the base of everything. Why are there different types? Depends on the soil.
Exactly. The ground underneath is just as important as the building materials. Different soils, clay, sand, rock, loam, behave differently under load. Some are strong, some are weak, some shift with moisture. So you need a foundation type that matches the soil and the weight of the building.
Okay, so engineers have to figure that out first.
Absolutely. Soil testing is a crucial first step.
Let's look at raft foundations. When would you use those?
Raft foundations are typically for when the soil is weak or maybe inconsistent. Instead of just supporting columns or walls, you build one large, continuous slab, like a raft, under the entire building.
Ah, so it spreads the weight out.
Precisely. It spreads the building's load over a much bigger area, which reduces the pressure on the weak soil underneath. It helps prevent the building from sinking or settling unevenly over time. Super important for longevity.
Makes total sense for soft ground. What about the opposite, maybe pad foundations?
Pad foundations are more like individual feet under specific load points, usually columns. You use these when the ground is strong enough to take concentrated loads. So you might see them under the columns of a steel-framed warehouse or maybe an office building.
Okay, so individual supports on strong ground. Then we have shortboard piles. That sounds like you're going deep.
You are. You use piles when the soil near the surface is too soft or loose to support the load. So you drill or bore holes down through the weak stuff until you hit a firmer layer, stronger soil or rock, and then you fill those holes with concrete.
Like putting down stilts to reach solid ground.
That's a good way to think of it, yeah. Anchoring the building to something solid deeper down, necessary when the surface just won't cut it.
Okay, now this one sounds interesting. Stepped strip foundations. For sloping ground, I'm picturing steps.
You're right. Imagine trying to dig a level trench for a foundation along a hillside. One end would be way deeper than the other.
Yeah, tons of extra digging at the deep end.
Exactly. So, with a stepped strip foundation, you dig a series of level steps that follow the slope. Each section of the foundation trench is horizontal, but they step up or down the hill.
Ah, okay, so each part is level, but the whole thing follows the slope. What are the advantages?
Two main ones. First, keeping each section at a consistent depth ensures the foundation has uniform strength and stability all the way along. Reduces the risk of problems caused by uneven settling.
That seems important. And the second?
Second, it saves a lot of digging and concrete on the higher parts of the slope compared to digging one massive, deep-level trench. So it's more efficient, saves time, effort, and money. It's just a smarter way to build on uneven ground.
Clever. Okay, so we've got our solid foundation. Now we go up the structure itself, the skeleton or the main walls.
Yeah.
I gather there are two main approaches.
Broadly speaking, yes. You've got framed building structures and solid building structures. Two different ways of thinking about how the building holds itself up.
Let's take frame structures first. What defines those?
Frame structures use a skeleton, usually steel or reinforced concrete beams and columns, to carry all the main loads, the floors, the roof, everything. The walls in these buildings often just fill the gaps. They aren't usually load-bearing themselves.
Like our own skeletons carrying the weight.
Kind of, yeah.
What's the big plus side of building like that?
Flexibility is a huge advantage. Because the walls aren't holding the building up, you can often change the internal layout much more easily later on. Knock down walls, move them, add new ones. It doesn't mess with the structure. Right.
Oh, okay. So good for buildings that might need changes, like offices or factories.
Exactly. Perfect for spaces that need to adapt over time. But there's a flip side, right?
There usually is. What's the challenge with framed structures?
The connections. The joints where the beams and columns meet have to be incredibly strong and engineered just right. That often means you need very skilled workers and really strict quality control during construction. It can add complexity and cost.
So the strength is all in those connections. Got it. Now the other type, solid building structures. How are they different?
In solid structures, the walls are the structure. They're the load-bearing elements, usually made of brick, concrete blocks, or maybe poured concrete walls. They support the floors and roof directly.
Okay, so the walls are doing the work. What are the benefits there?
Well, they tend to be inherently very strong and often provide really good insulation, both thermal keeping heat in or out and acoustic blocking sound.
Ah, good for houses then. Keep them warm and quiet.
Yes, very common for residential buildings or anywhere where insulation and soundproofing are a priority.
Makes sense. What's the trade-off with solid structures?
The main one is the lack of flexibility later. Because those walls are structural, you can't just easily knock them down or move them. Changing the layout becomes a major, often expensive structural project.
Right, so you trade that easy adaptability for the built-in strength and insulation. Interesting choice. Okay, let's move right up to the top of the roof, keeping the weather out. I see a difference noted here between hip roofs and gable roofs based on rafters.
Yeah, the rafters are the sloping timbers that form the roof's shape. The arrangement dictates the style. A hip roof has slopes on all four sides of the building.
Okay, like a pyramid shape almost.
Kind of, yeah. It uses diagonal rafters called hip rafters that run from the corners up to the ridge, and shorter hip jack rafters that fill in between the hips and the wall plate. The wall plate, by the way, is just the timber beam sitting on top of the wall that the rafters rest on.
Got it. 4 sloping sides. So how is a gable roof different?
A gable roof is simpler. It only slopes on 2 opposite sides. The other 2 ends are vertical triangular walls called gables. It mainly uses common rafters that run straight from the ridge board at the peak down to the wall plates on those 2 sides.
Ah, the classic house-shaped roof. 2 slopes and 2 flat ends.
That's the one.
Okay. Now, what if you have a more complicated building shape, say like a T shape?
Hmm.
How do you roof that effectively so water runs off properly?
Good question. With complex shapes like a T, you typically end up intersecting roof sections. So you might have two gable roofs meeting, or maybe a hip roof intersecting with a gable. The key is designing the slopes and the valleys where the different roof planes meet so that rainwater is channeled away efficiently from all surfaces.
Right. You don't want water pooling anywhere.
Definitely not. That's asking for leaks. So careful planning of slopes and valleys is crucial for complex shapes.
And there are specific names for these roof parts. Can you run through a few key ones?
Sure. We mentioned the ridge board, that's the horizontal beam right at the very peak. The hip rafter is that diagonal one on a hip roof corner. Hip jacks are the shorter ones connecting the hip to the wall plate. And common rafters are the standard ones going from ridge to wall plate on a gable or hip roof. Oh, and the wall plate sitting on the wall.
Helps to visualize how it all goes together. And constructing one, say, a hipped roof with valleys, what's the basic sequence?
Usually you start by getting the ridge board fixed in place, nice and level. Then you'd install the main structural lines, the hip rafters, and any valley rafters where internal corners meet. Once those are set, you fill in between with the common rafters and the jack rafters to complete the frame.
Build the main lines, then fill in the gaps. Makes sense.
Hmm.
Now, what about the actual covering? The stuff that keeps the rain out? Different options there, too, yeah.
Oh yeah, lots of options. Shingles are very common, things like asphalt or tile,
Yeah.
give a neat appearance and are generally very good at waterproofing.
Looks good, keeps water out, both important. What about corrugated sheeting? Like metal roofing?
Right, corrugated sheeting, often metal, sometimes plastic. Its big advantages are that it's usually very lightweight, which makes it easier to handle and put up, and it can be installed quite quickly.
So potentially faster and maybe cheaper installation.
Often, yes. Saves on labor time.
Any downsides to the corrugated stuff?
The main one people notice is noise. When you get heavy rain, it can be quite loud inside compared to shingles or tiles, the drumming sound on the metal.
Yeah. Maybe not ideal for a bedroom then.
Probably not, depending on your tolerance, so you weigh the pros and cons based on the building's use.
Right. Okay. Changing gears a bit now, but still essential.
Mm.
Dealing with waste and getting water in. Sewage disposal first. What are the main ways we handle that?
Generally, two main systems. You either have a septic tank, which is basically a private on-site treatment system for a single building or a small group, or you're connected to the public sewer system, where the wastewater flows through municipal pipes to a larger centralized treatment plant.
So local treatment versus a big network.
Essentially, yeah.
Yeah.
Decentralized versus centralized.
Now, for the pipes bringing water in and taking waste away, lots of different materials used.
Yes, different pipes for different jobs. You've got things like galvanized steel that's steel-coated in zinc, used mostly for cold water, joined with threaded fittings. Less common now, maybe.
Okay. What else?
Copper is very common. Good for hot and cold water. It's usually joined by soldering the fittings, which makes a really strong, reliable joint for pressurized water. Needs a bit more skill, though.
Right. Soldering takes practice. Plastic pipes.
Lots of plastic now.
Oh,
PVC polyvinyl chloride is common for cold water supply and also for waste pipes. You usually join it with special solvent cement in sockets or sometimes threads. Then there's CPVC, chlorinated PVC, which can handle hot water too, unlike regular PVC. Similar joining methods.
so the type of water, hot, cold, waste, and the pressure really dictates the pipe material and how you join it.
Exactly. You choose the right tool for the job.
And what about all those little connector bits?
Mhm.
Fittings, elbows, traps?
Mhm.
What do they do?
Fittings are crucial. Traps, usually U-shaped pipes under sinks and drains, are really clever. They hold a bit of water constantly.
To block smells.
Precisely. That water seal stops unpleasant sewer gases from coming back up the pipe into your house. Simple, but essential for hygiene.
Definitely appreciate those. What about elbows?
Elbows just change the direction of the pipe run. 90 degrees, 45 degrees. Lets you route the pipes around corners and obstacles.
And valves.
Valves are like taps or gates inside the pipe. They let you control the flow, turn it on, turn it off, maybe adjust the pressure. Think of the shut-off valve under your sink or the main water valve for the house.
Right, for control in emergencies. And T's.
T's are T-shaped fittings. They let you split one pipe run into two, branching off the supply to different fixtures, like sending water to both the hot and cold taps from the main lines.
Okay, so each fitting has a really specific, important job in making the whole plumbing system work.
Absolutely, it's a whole network.
Well, this has been quite the journey. From digging foundations and mixing concrete right up to roofing and plumbing. It's amazing how all these different elements have to come together.
It really is. You start to see how interconnected everything is. The strength of the foundation affects the structure holds up the roof protects everything, and the plumbing makes it livable. It all has to work as a system.
A system for creating stable, functional buildings that we rely on every single day.
Exactly. From the simplest shed to the tallest skyscraper, these fundamental principles apply.
Absolutely. And thinking about all that complexity, even in what seems like a simple building, it makes you wonder, what's one piece of this construction puzzle that you, listening now, maybe see with a bit of fresh appreciation?
Yeah, maybe next time you walk past a building site, or even just look around your own home.
Take a moment, think about the foundation you can't see, the frame or walls holding things up, the roof keeping you dry, the pipes bringing water.